Hi, I'm Tim Lynch. My sponsor is the Department of Energy, and my project title is In Situ High Temperature Measurement and Validation of Uranium Molten Salt Properties. So the problem statement is to determine properties of model molten salts at operationally relevant temperatures in preparation for uranium fuel salt experiments. So the DOE is interested in molten salt reactors because of safety benefits over traditional light water nuclear reactors. But a lot of research needs to be done on many components of the MSR before they can be implemented in the public or for energy use. One of those areas is the salt properties themselves. So we're doing experiments at Stanford Synchrotron Radiation Light Source. It's a DOE lab run by Stanford University. And what a synchrotron is a particle accelerator that produces X-rays from 5 keV to 35 keV. And we're using X-ray absorption fine structure spectroscopy to find salt properties. So from that, we can determine formal oxidation state, coordination chemistry, coordination number, radial distances, and speciation. So how it works is we're shooting energies in steps starting below the binding energy of electrons in an atom, up well past the binding energy for however much data is desired. And the phenomena that you're seeing in this graph to the right here is an absorbance edge, which is a large increase to the absorbance at binding energy electrons. So on the y-axis is absorbance, on the x-axis is energy. So here's the absorbance edge right here. And that basically is what the photoelectric effect is. So you're seeing that phenomena right there. So the samples that we're studying are a chlorides mix, which is shown here, and a fluorides mix, which is shown here. And these are model salts to test the efficacy of the experiment for future uranium-containing experiments. So the experimental setup, how it works is the salt is in a boron nitride test tube, cemented down with a boron nitride cap to seal it, and it's surrounded by a molybdenum disilicide resistive heating element to heat it up to whatever temperature we want. Now, before and after the sample, there's detectors. So the initial detector detects 100% of the incoming X-ray, and then some of that X-ray gets absorbed in the sample, and then the detector after it detects how much X-ray is left over. So, and that is how the absorbance spectra is created. So how the experimental procedure works is that we're heating until a steady state temperature is reached, and then we conduct scans. So we do 3 to 4 scans per temperature, and we're doing temperatures from 25 degrees C up to 1100 degrees C in 200 degrees C increments. And then again, once the sample is resolidified at room temperature. And just to give you an idea, these salts melt between 800 and 900 degrees C. So here, they're melted up at these temperatures. Down here, they're not, and down here, they are also not melted. So now the chlorides, I'm going to show you some results that we found from our experiments. So here, we see that from our data, we found that our spectra changed shape quite a bit from what we saw in previous scans, and we think that is due to hydration. So you can see from D'Angelo et al., this is a hydrated strontium spectra, and you can see the features of this hydrated strontium spectra match exactly with our resolidified spectra. So we think that water from the water-based cement that was used to seal down the cap leaked into the sample and caused the sample to become hydrated. So now the fluorides, I'm going to talk about some results from those experiments. So when the salts melt, you would expect that longer bond lengths to break down. But in fact, at and above the melting temperatures, we see that that didn't happen in our experiment. So you can see there's a long bond length of 3 angstroms. So ideally, these would be flat after this large peak here. But it's not. So what we think happened was possibly the formation of a stable ternary compound, Li3ZrF7, determined from lithium zirconium fluoride phase diagrams. Now, there's no structural information for Li3ZrF7 in the literature or anywhere really. It's never been tested. So what we did was we compared data with other ternaries to show peak at 3 angstroms is probably due to ternary forming. So in the blue is our data, and in the red is the various ternaries. So the various ternaries are Li2ZrF6, Li3ZrF19, ZR4F19, and Li4ZrF8. And you can see here on the left, there's a peak of 3 angstroms. Here in the middle, this shows a nice qualitative resemblance to our data, and there's also a peak at around 3 angstroms, and then here in the last one, there are 2 peaks that are at about 3 angstroms or pretty close to it. Thank you for watching. Hope you have a good one.